A totally normal ringtone. All right. Okay. All right. Well, we'll begin. And happy Halloween. So this week we'll take a look at some statistical concepts and statistical foundations. How many of you have taken like AP Stats? Okay. Oh, well, a lot of you took it. Okay. All right. Well, great. Then we can. Well, good. I'm skipping a whole bunch of stuff, right? We spend a lot of time the first 5 weeks covering like how do you manipulate a data frame in R? How do you manipulate a table in R? And that's very important because as you start working through your data sets, like you need to be able to do that. You need to like just learn how to handle some of these tools, right? And then once you understand how to handle the tools, then we can start working towards statistical inference. In your traditional like AP Stats class, who has not taken like an AP Stats or an Intro Stats? Okay, so a handful of you. Don't worry, okay? All right, so in your traditional AP Stats class, or a Stats 10, so if you take Stats 10 at UCLA, it covers, I'd say like 75-80% of what AP Stats covers, and it compresses it all down into 10 weeks, right? So, but it covers kind of a lot of these kind of traditional core concepts, like what is a sample, what is a population, how do you calculate the mean, how do you calculate the standard deviation? Let's learn to make a box plot by hand. Let's learn how to draw histograms by hand, and a lot of kind of these things, and I've kind of skipped a lot of that by just saying like, here's the tools, here's your computer, and like if you want to make a plot, here's ggplot, here's some commands here and there. Okay. One of the core ideas is, how do we say make comparisons based on data, right? Or how do we look at data and draw meaning and inference from it? And so one of the key ideas that you get to in, say, an AP Stats or a Stats 10 course is the t-test. It's the idea of comparing two samples and comparing the means of two groups. Okay, so we'll start here. And so this is just my made-up scenario, okay? And so, sometimes you go to the grocery store or the, department store like Target or something like that, and, you want to buy some batteries, and you got like the name brand, you have like Duracell and Energizer, and you see commercials for those batteries on TV, okay? But then you also see like, batteries that look like this, right? These are like your store brand batteries. You've never seen a commercial. You've never seen a commercial for Best Buy brand batteries. But you go to the store and you go, oh yeah, I guess those are batteries, and they'll probably get the job done, right? And the question, there's always kind of this question like, oh, these are so much cheaper, or a lot of times they're so much cheaper, like, are they just as good? Or in fact, is there even a difference between these things, right? And so let's just say you buy two of these things, brand A and brand B. It doesn't matter, okay? It doesn't matter. And then a friend says, oh yeah, all those batteries, they're like made by the same company, and all they do is they just change the label. And you go, oh, I guess that makes sense. It's not like Target's gonna start its own battery company making like its secret, batteries or something. But you're kind of like, oh, well, maybe there's like multiple of these things. Maybe there's different factories. Maybe like Best Buy is like, when you make batteries, we only want the good ones. Give your crappy batteries to, some other store. Okay, I don't know, right? So you say, well, let's do a little experiment, okay? Now, actually setting up the contraption for this experiment might be kind of difficult. Just go with me and pretend like we were able to set up some kind of contraption that does this and measures things, right? So we're gonna decide to run an experiment to see if you can kind of confirm or deny your friend's claim. And you build some small electronic contraption, right? So you plug a battery in, maybe it spins a motor or a fan or whatever. It's also measuring the voltage across the battery, and it measures like how long, how much output it's done. Okay, I completely made this scenario up, and I completely made up this data here. Okay, but so let's say so when anytime you do an experiment, a key idea is you need to have everything, all of your parameters, like very clearly defined. Like when you say like how long does it go until the battery is dead, you need to have a definition for what it means for the battery to be dead. Okay, and perhaps that means the voltage reaches 1.35 volts or something. A lot of that's a lot of times like low enough where like things stop working and stuff, or you get your low battery warning on your camera or microphone or whatever. You just have some contraption that's going to kind of run consistently, and you're going to measure how long it takes. And then so we have 12 batteries from brand A, and the first battery ran for 135 minutes, so 2 hours and 15 minutes. We get another battery, it runs for 138 minutes. Another battery runs 122, 128, 114, 123, 137, 113, 115, 116, 120, 115. These are the numbers. Okay. You take the average of everything from brand A, the average is 123 minutes. Okay. We've got 12 batteries from brand B, and they are 132, 122, 127, 130, 134, 117, 117, 131, 142, 132, 131, and 133. And the average runtime of these batteries is 129 minutes. Okay? So you ran these, you did this, you ran 12 batteries for brand A, 12 batteries for brand B, and you do this thing, right? Okay, so if this is like your 5th grade science project, you'd draw a little poster, and you'd have batteries, and then you'd have a little bar graph that says brand A 123, and then brand B 129, okay, which is taller. And then you'd say, what would your conclusion be? Is brand A better than, or is brand B better than brand A? And you'd say yes, no. You'd say 129 is bigger than 123, and that would be like your science experiment, your science fair project in 5th grade, and and probably it would come down to like what kind of contraption did you build, and they'd be like, ooh, good job, you built a circuit and you had a I don't know, whatever, right? If you have a voltmeter in your science fair project, it's like, ooh, that's cool. But anyway, you'd say 129 versus 123. 129's bigger than 123, so it seems like you're going to get 6 minutes of extra runtime out of battery B versus battery A, brand B versus brand A. Okay, but here's the thing. Okay, here's the thing. In statistics, we say there's randomness. Okay, you look at these individual batteries within brand A, and you know what? Some only ran 113 minutes. This was a low performing battery, okay? And then you have some batteries, even they're brand A or whatever, they ran for 138 minutes, okay? And then you look at brand B, and you have 117 on the low end, you have 142 on the high end, okay? So those are like well above or below these kind of averages of 123 or 129. And so the question is, I wonder, could what we see be the result of just kind of randomness, right? Like, so one conclusion we can make is like, does brand B have a mean time? Does this mean that brand B has a mean runtime that's different from brand A's runtime, and kind of thus indicating that they come from different companies? Or is it possible that brand A and brand B actually, they come from the same company, they have the same mean runtime, but just kind of by random chance, like when you bought your batch of batteries from brand A and your batch of batteries from brand B, like you just happened to get kind of some junky batteries in brand A, and you kind of got some, good batteries in brand B, and like because of that, you happen to get, 129 over here and 123 over there. Is that also possible? Okay. So that's kind of the core question. And here I'm doing batteries, but it could be like any other kind of thing, right? So you could have, as you are doing your projects, okay, you'll probably say, here's this categorical variable, and we can split our data, right? And we can say, okay, here we have group A, and here's group B, right? You can, maybe you have genders in your data, and you can have, male or female, and split your data into that, okay? Or maybe you have, maybe different countries represented, and you can say, here we have, people from the U.S. versus people from Canada, or I don't know, whatever's in your data. You might say, okay, here's something interesting. These are houses in, you could even take a numeric variable and split it, right? And you can say, let's just split at the median, okay? And this is like houses that were priced below the median versus houses that were priced above the median, or houses that had, square footage below the median or square footage above the median. And is there, a difference, between these things, or is it could it just be because of randomness, right? So as you work with your data sets, you could take a numeric variable and mutate it into like a categorical thing of like, is it greater or less than something? And then you can kind of split it into two groups, or whatever it is, right? Here I'm just doing brand A versus brand B, but you could imagine in your data you have different groups and you want to compare the means, okay? And so here I'm doing 123 versus 129, and it's not enough to just say, hey, there's a 6-minute difference, okay? We want to know, could we get a difference of 6 minutes just kind of by like randomness, right? Is this second scenario possible, that they actually do come from the same factory, same mean time overall, but just by randomness, we got some, lesser performing batteries in group A and better performing batteries in group B. Okay, so this is kind of where we bring around a hypothesis test. Yeah, question?
More like a general question. It's like when they say sample size, is that just one? Are we looking at one individual sample and see how many batteries they took, for example, or is it how many times they performed this like sample?
Yeah, well, it depends on the experiment. So here, I took a sample of 12 batteries. I'm assuming the pack of batteries I bought is like a random sample of batteries, and so that's going to represent my sample. I've got a sample of size 12 for brand A, sample of size 12 for brand B. They don't have to necessarily be equal. I just picked two samples that were equal, but they don't have to be. But in other cases, your sample could be like repeated trials. So depending on the scenario, rather than it could be like what is my own performance or something. Like on days where I got 8 hours of sleep before, I go running and I measure how fast I can run. Okay, and you do this like on 10 days, and then you do like on days where I only got 6 hours of sleep before, how fast can I run, right? And is there a difference between my performance when I get 6 hours of sleep versus 8 hours of sleep or something? And here you're just kind of doing the same thing, and it's going to take you like a month to collect all that data. Okay, but you could do that. So that's a sample. You have a sample of 10 and 10 or whatever. Also fine. It's just how do you define what each observation is? In this case, each observation is a battery. In other cases, each observation might be a person. In other cases, it could be each observation is the outcome of one experimental trial.
It'd be like a pack of batteries, and you buy multiple packs.
Well, are you measuring the entire pack all at once? It could be like I'm buying a pack of 4 and I have a device that uses 4 batteries all at once, and we're going to do like all 4, and that would be like one pack versus another or something. Okay.
Yeah. Thank you.
So this this question of comparing two means, okay, we're going to use a hypothesis test. And specifically for this one, when we compare two means, it's going to be the two-sample t-test, right? And I think I'll probably just introduce like maybe a handful of statistical tests that probably are going to be like most relevant or most useful. So comparing two means is like a very common scenario. Maybe I'll also do like comparing two proportions or something, or I guess proportions that we might observe with like a chi-squared test or something. Okay, so hypothesis testing in general is a framework for us to make conclusions about the population. Okay, so those of you who took like AP Stats, can you define what a p-value is? Yeah.
Isn't a p-value kind of just like a measure of how likely it is that we get a result based off of random chance as opposed to actually being statistically significant?
I think yeah, so it's a probability. It's a probability of what would you say?
I'll give it a shot. I'd say it's the probability that given any sample, that the results you got from that sample are due to chance rather than an actual variation between the two variables.
We've got a lot of kind of the right ideas here, but there's a subtle difference between your answer and what I think what you're saying versus like what I'm going to define here. Okay, so here let me back up, and we'll just kind of we'll go through, and then we'll try to pick apart what some of these differences are. Okay, so we take these, we take our research question, and we have to take our question and state it as a testable hypothesis. And we call this thing the null hypothesis. And I guess that's why we call it hypothesis testing, because we're going to be testing this hypothesis that we make. For a hypothesis to be testable, it has to be a specific claim, right? In order to kind of be able to prove or disprove something, it's got to make a specific claim. If somebody just makes vague statements, like, it's difficult to disprove them when they're vague, and but it's also like you can't really like prove it's true, right? So like, if you were to go visit, a fortune teller or psychic or something, they flip their cards over and they say, oh, you're gonna meet an interesting person who made a long journey and in the coming days, right? And that's like so vague, and it's like, what do you mean by a long journey? Okay, and it's like, is that like coming from San Diego, or is that like coming from China or something, right? So interesting person, how do you define that? It's so vague that it's like almost anything can kind of qualify to meet this thing. Versus if somebody makes a very specific claim and says, you're gonna meet within 3 weeks, you're going to meet a traveler from, Australia, this specific country, and their name's going to be Doug or whatever, right? It's a very specific thing, and you can see like, okay, did this actually come true or not? That's something we can test. All right. So in this case, our specific claim is going to be that we have two kind of populations. The idea is a population is everybody that would answer a question, but we're not able to observe them directly. So in our case, the populations are olive brand A's batteries and olive brand B's batteries. And the null hypothesis is that these two populations have means, and those means are exactly equal to each other. So it's a very specific claim that mu1, the mean of population 1, the symbol for the mean is mu1, and the mean for population 2 is mu2. We're saying these two means are exactly equal. Or specifically for this problem, we're going to say if we were to measure all of brand A's batteries, okay, we would get a mean runtime of, I don't know, some number, okay? Let's say it's 126, all right? And if we measured all of brand B's batteries, all right, we would get the exact same number. That's what we're saying. These two brands, if we measured them all, we would get the exact same number. The problem is we can't measure them all, right? We can't measure them all. We'd have to like shut down, I don't know. We'd have to buy all the batteries in the world, okay? I'd have to go to like every single Kroger and go to their, I don't know, battery aisle and buy all of their batteries and measure all of these things. And it would just, I don't have time for something like that. Or the money, right? Even though they're only $3.99 for a pack of 8, I'd have to buy 1 million of these things. I don't have that kind of money. So I can't measure all the batteries. I have to make do with my sample of 12, okay? Maybe if I had a little more money, I could do a bigger sample. But right now I have 12 from each brand, and I'm hoping that these 12 are representative of the entire brand, okay? And so when we test the hypothesis, we start off and we say, let's assume this claim made by the null hypothesis is true. Let's assume that, yeah, brand A and brand B, they're like basically coming from the same factory. Their run times are exactly the same if we measured all of them, all right? So if brand A and brand B truly do have the same mean, when I run my experiment with random samples of batteries, what would we expect? What would we expect to see? What we would expect to see is that the run times for these two groups of data are going to be equal to each other, or at least close to equal, right? So when you assume the null hypothesis is true, you have to just imagine this hypothetical situation where, yeah, actually brand A and brand B do have the same mean. Okay, questions?
Do we get to determine how close is fairly close to equal?
Yeah, that's where the t-test comes in. Okay? Yeah.
So these are both continuous variables. Wouldn't it be like physically impossible for the means to be exactly the same because it always just goes down?
Yeah. So right. Okay. So right. They are continuous variables, and I measure them to the nearest minute, but if I had a really precise thing, I can measure them, 123.117 minutes or something like that. And if we take the average, we probably won't get two means of random samples. We'll never actually be exactly equal. But if they're off by like 3 seconds, we'll say that's close enough, okay? That's close enough, right? Okay? But yeah, there's kind of this idea that again, in this hypothetical world where brand A and brand B are the same, okay? And we just happen to like randomly get some batteries over here and randomly get some batteries over here, what does this world look like? Well, what that world looks like is that when you take random battery A and random brand B, your averages should be close, like either equal to each other, at least very close to each other, all right? And the question now becomes, all right, we got a difference of 6 minutes. Is that still fairly close to each other? Or is that like different enough where we're like, okay, there's a difference here, right? That's what we're trying to distinguish, right? And right now, we don't know the answer off the top of our head. Just looking at these numbers, we look at this and we go, okay, 123 versus 129, there's a difference of 6. We're like, okay, looking internally, like how much, like if every number in brand A was exactly 123, like all the batteries in brand A was what, 123, 123, 123, 123, and everything for brand B was 129, 129, 129, there's like no variation there, we'd be like, okay, definitely different. Brand A is consistently 123, brand B is consistently 129. But here we see, oh, you know what? Sometimes brand A goes as high as 138, sometimes as low as 113, or I don't know, whatever, if there's higher or lower numbers, right? And so we say, okay, well, you know what? Maybe there's enough kind of like, fuzziness, okay? Just variation within the data that we could have gotten this difference of 123 versus 129 just kind of by randomness, right? So, when we look at our data, the batteries from brand A have a mean of 123. The batteries from brand B have a mean of 129. these two samples don't have the same mean, there's a difference of 6 minutes between the two, okay? If the null hypothesis were true, I would expect the difference to be 0 or close to 0, okay? Probably we can't expect it to be exactly 0, right? Again, because like, you know, if you pick random people, you're not going to get like the exact same average, but you'd expect them to be kind of close, right? And the question is 6 minutes kind of close or not? So I think that's what I wrote here. If brand A and brand B, or more generally, population 1, so again, in your scenario, you'll have just group 1 and group 2, or population 1 and population 2. If they do actually have the same mean, what's the probability that just kind of by randomness alone, we get a difference of 6 minutes between the two averages, okay? And so we have to do some calculations, all right? And so here, the answer to this question, what is the probability that randomness alone could produce a difference of 6 minutes or more if the null hypothesis were true? That is the p-value, okay? So it's like, well, how's that different from anything that anybody else stated? So the p-value doesn't actually tell you how likely something comes from random chance. It's so that, like, if you get a p-value of like 10%, it doesn't mean there's a 10% probability that it came from one scenario or another. It's indicating if the null hypothesis were true, how often does randomness produce this result? Let me talk a little bit more, and maybe that's what you said, and I didn't quite hear it. But this is what I'm writing here. Okay, the p-value is going to be the probability of observing the statistic in our data, in our case 6 minutes, okay, or something more unusual if we assume the null hypothesis is true. So in our case, it's what is the probability of getting a difference of 6 minutes between these two samples if they're all actually the same battery, okay? If brand A and brand B are the same, can you get a difference of 6 minutes by randomness? And the answer is yes. And if so, how often does that happen by randomness? And that's going to be the p-value, okay? How often do we get a difference of 6 minutes just by randomness? Because frequently, you'll get a difference of probably like 1 minute or more, and that's going to happen a lot, right? So the p-value of getting a difference of like 1 minute or more, just by kind of randomness, you'll have a high b value, right? What's the probability you're going to get a difference of like an hour by randomness, right? So if brand A and brand B are the same battery, all right, if we just all the batteries are coming from the same place and we just dump some over here and dump some over here, are you going to get a difference? You know, the average runtime over here is 60 minutes and the average runtime over here is 2 hours. Is that going to happen by random chance? Not really, right? Probably not, okay? But what about a difference of 10 minutes? What about a difference of, 5 minutes? What kind of differences can we get? The probabilities of that outcome will be our p-value. Oh, you know what? I always forget about my view quiz answers. Let me give you your first two. D is your first one and A is your second. D as in dog is your first view quiz answer. D as in dog. Your second view quiz answer is A as in apple. D as in dog, A as in apple. Okay, so we could go through our calculations. All right, so before we even run the t-test, let's just talk about what scenarios we get, all right? Let's say we do our calculations and the p-value ends up small, all right? And it says, if the population means are equal, can you get a difference of 6 minutes by like just randomness? And it says it's possible, but there's a small probability. Okay, and therefore, and here's the reasoning here is we actually observed this difference of 6 minutes, okay? So in this hypothetical world, it says if the brand A and brand B come from the same factory, and in that world, getting a difference of 6 minutes is really unusual, okay? In that world, getting a difference of 6 minutes happens maybe like 1% of the time, okay? So here we are in our world, the real world, and we got brand A, 123, brand B, 129. We got a difference of 6 minutes. And we could say, okay, well, maybe we are in this hypothetical world. Maybe we're in the world where brand A and brand B do produce the same results, and we just got that really lucky 1% sample. That could explain it, right? We were just at 1% of random samples produce a difference of 6 minutes, okay? So it's not impossible, it's just unlikely, okay? Or perhaps the easier explanation is you're not the lucky 1%, okay? The reason why you're getting a difference of 6 minutes is because brand A is worse and brand B is better. That's why you're getting a difference of 6 minutes, okay? You aren't the lucky random sampler that went along and happened to just by random chance get the crappy brand A batteries and by random chance the bad batteries ended up brand A and the good batteries ended up brand B. No, the reason why you're getting a difference of 6 minutes isn't because they're equal, it's because they're actually unequal, all right? That's a little bit easier, perhaps, to swallow, okay? So in that case, we would reject the null hypothesis, all right? Okay. The other possible outcome is you do your calculations and your p-value ends up like a huge number, okay? And it says, yeah, if the population means are equal, a difference of 6 minutes is likely, it's just not unusual, okay? It's like if you flip a coin 20 times and the coin lands heads 11 times, you're not going to suddenly go, oh my gosh, I have a trick coin, all right? I got 55% heads. 11 divided by 20 is 55% heads, okay? I got 55% heads. I think my coin is, biased to land heads more often. You just be like, oh no, that kind of stuff happens because it's random, right? You can't expect to get exactly 10 heads and 10 tails every time. And you'd say, oh yeah, sure. You do your batteries. Yeah, sometimes you're going to get a sample where the mean is high and a sample where the mean is low. And a difference of 6 minutes, it's not that big of a deal, okay? That's the other possibility here, right? You can do this and it says, yeah, stuff like this happens like 20% of the time, okay? Just by kind of randomness. And so, we would expect the means of our samples, x bar A minus x bar B to be close to 0. We get a difference of 6 minutes, which is more than 0, but according to our calculations, this kind of difference isn't considered to be unusual. So at that point, we have no reason to believe that mu A is different from mu B, okay? But at the same time, it doesn't mean that the two means are actually equal. It just means at this point in time, we don't have enough evidence to make the claim, right? So we do not reject the claim made by the null hypothesis. All right, so what is a large p-value or what's a small p-value? That's determined by this thing called the significance level, and it's just, we give it the letter alpha, and it's just an arbitrary kind of line in the sand. If the p-value ends up less than alpha, we say the p-value is small, and we would reject the null hypothesis. And if the p-value ends up greater than alpha, we say the p-value is big, and we don't reject the null hypothesis, all right? Common choice for alpha is 5%, but you can also have alpha 1%. You can also, you can have alpha 10%. I'd say that's pretty uncommon, okay? So most frequently we use alpha around 5%. And it's just kind of an arbitrary line, all right? Probably because we have 5 fingers, all right? But something around there. There's probably, something around there is probably right. It's just like, you're considered an adult when you're 18. It's just an arbitrary number. And and everything goes off of this, okay? No, and we've accepted this, right? And it's like, oh, you turned 18, you can go ahead and buy, a gun or something and join the army and stuff. Whereas could it be higher? Some countries, age of majority is 19. Some countries, it's age of 20, right? And, they hear, in those countries where the age of majority is 20, they go, oh, 18. Ooh, that's weird, right? Or something, okay? It's an arbitrary line, but it's not like suddenly, someone who's 17 years old and 364 days is, going from one day older suddenly makes them super mature, and now they can be trusted, with, taking out not $1 million, but like, hundreds of $1,000s in school loans, right? We say, oh, you're 18. Yeah, sure. Go ahead, sign the line. And we expect you to, you're responsible for all of these financial decisions yourself, right? Whereas if you did it 2 days before your 18th birthday and the bank told you to sign on the line, then you could say, hey, you can't hold me legally responsible for this, right? That would be the bank's fault for not making sure you were old enough or, mature enough to kind of do these things. But that's, again, arbitrary line. Is it that something magical happens at 5%? No. Okay? We've agreed, or a lot of people have agreed, this is the line. As far as laws go, we have to make a number and things like that. You can't just say, oh, we felt like this person was mature enough to sign away, $80,000 in debt, or something like that. But yeah.
Since it is kind of like random like that, in actual like statistics in the field, like will people kind of generally do more than just like a statistical significance test like this, because you're inherently like if you get like a 5.1%.
Yeah, it depends. And so you do see like some weird things happening. Like you'll see there's a lot of articles getting published where the p-value is like 0.049. Like they just barely made it under the 5% cutoff where it's small, and so you have a bunch of things where it's just like, okay, it just got under that 5%, so now we can say it's small and reject the null hypothesis, right? And it's kind of like people do like celebrations right on their 18th birthday, and then they go buy lotto tickets, or I don't know, what else can you do when you're 18, right? It's like, oh, it's a big deal right as soon as you hit this number. Yeah.
Setting the p-value also kind of depends on the situation, right? Like 0.05 might not be ideal for like medical trials where like 5% of that good isn't a great idea, but like maybe 5% is okay for other things.
Yeah. Again, we can talk about when 5% is a good number or bad number or something like that. Okay, but it's, again, this is kind of the common choice, but it's a little bit arbitrary, right? And it's not like this is necessarily the best, right? And it's not like every single person who turned 18 has the mental maturity to make all of these decisions, right? Okay. Hypotheses are always statements about the populations. Let me kind of just skip overhead so I can get to what this goes to. So I've got directional and non-directional alternatives. I want to get to the results. So here we have a non-directional. It'd be interesting to us if brand A outperforms brand B. It's also interesting if brand B outperforms brand A. You might have something called a directional test where you're only interested in one side, right? So let's say you want to compare like brand name Duracell against the store brand batteries, okay? And so in that case, you're like, the question is like, is it worth paying the extra money for like better performance? And you want to kind of measure if if there actually is better performance. And let's say you do your test and it actually turns out like the Duracell or whatever like performs worse than like the generic brand, okay? Then it's like, okay, you know what? Don't even bother with the rest of the statistical analysis, because you're just not going to have evidence to support this kind of thing, okay? All right. So anyway, here's our data, right? We took the mean 123. We took the mean of brand B 129. Difference of 6. We can also calculate a standard deviation for brand A and a standard deviation for brand B. 9.33, 7.25, okay? Sample size is 12 for each of these things. The hypotheses would be mu A, all of brand A batteries, okay? is the mean runtime for all brand A batteries and mean runtime for all brand B batteries. We're not able to find these means directly because we can't measure all the batteries out there. Okay, and the null hypothesis says that these two have the same mean runtime, and the alternative is that they are different. Okay, and the p-value here is what is the probability that we would get a difference of 6 minutes if in all the batteries of brand A and brand B actually are pretty much the same. Okay, if brand A and brand B are actually the same, could you get a difference of 6 minutes by random chance? That's when we do the t-test. Okay, so this is what the test looks like in R. You put your data into a vector. I have a vector A, which has their values. I have a vector B, which has their values. Okay, so here I typed in the numbers. You don't have to type in your numbers, right? You can use filter, so just kind of say filter for group A, and then you can select the column that you want, and then you can do pull. And when you do that, you'll get a vector of those values in that column. Okay, you do the same thing for filter for group B, and you select the column and you pull them out into a vector. And so now you'll have two vectors. You store them somewhere, and then you just do t-test A comma B. Okay, t-test for group 1, t-test for group B. All right, and it tells you, it spits all this stuff out. The kind of key value here is p-value is 0.09335. So this is our p-value, around 9%. 9%, okay? So the top line says our p-value for this test is 9%. And this means that if the null hypothesis were true, then randomness could produce these two samples where the difference is 6. And the probability that this happens is something around 9%. Okay? So if there really is just one factory that's producing brand A and brand B, is it possible that just kind of by random luck, we ended up with 12 batteries in brand A that was 123 and 12 batteries in brand B with 129? Yeah, it's possible. How often does that happen? It happens random luck 9.3% of the time. Okay? Is that a big number or a small number? Well, it's not huge, but it's not small enough that we can ignore it, right? The threshold of 5%, so 9% is higher than 5%, so we're not going to dismiss this possibility. Okay? And so, if our p-value is large, it means our observed data, which is what we have, our observed data could be easily produced by randomness even while the null hypothesis is true. And even though we didn't get a difference of 0, we got a difference of 6, it's not considered to be unusual. And so in this case, we do not reject the null hypothesis. We'll say that with the data we've collected so far, we just can't make a definitive conclusion. It's possible that brand A and brand B have the same mean, and our data is the result of random chance. It's also possible that brand A and brand B don't have the same mean, and we just haven't collected enough data to figure that out. Okay, maybe bigger samples would answer our question. And so I kind of and another thing, you can never say we accept the null hypothesis. Right? We didn't reject the null. But this doesn't mean that the null hypothesis is true. We observed a difference of 6 minutes, and even though that 6-minute difference is not a huge deal, we can't just say that brand A and brand B do have the same mean. Okay, here's a thing. If I collected more data and I have 36 batteries from brand A and 36 batteries from brand B, and I get an average of 123 for A and 129 for B, now because I've got more data, this difference of 6 minutes is now more significant, okay? And you do go to the calculations, you get a p-value of 1% in this case, okay? Read the rest of my notes, okay? But I've run out of time. Let me go ahead and give you your last view quiz answer. Last view quiz answer is the letter E. E as in elephant. E as in elephant, okay? All right, we'll go ahead and end here. Have a happy Halloween, and have fun, stay safe, and we will see you on Wednesday. Some of you I'll see you before for the, because we're having meetings and stuff. So I'll see you on Zoom for some of your groups. But have a great day. We'll see you Wednesday.